Hello and welcome to this talk on our paper, Degrees of Second and Higher Order Polynomials, a joint work with Donghyun Lim. So I'm going to start slowly by recalling the usual definition and maybe a new definition of classical, that is of first order polynomials, and their degree by structural induction. Then we'll generalize that to Arctic polynomials, which are basically polynomials involving the maximum operation, and their asymptotics, which turns out to be asymptotically they coincide with ordinary polynomials. Then moving on to the second order polynomials, we're going to motivate them with applications from computer science and from hard analysis, that is calculus. Their syntax and their semantics and their degree defined, actually well defined by structural induction. And then we're already halfway through this talk, from which we'll then proceed to the third and higher order case. And in order to do so, it turns out that the composition operation on polynomials will be crucial. Actually, there will be several composition operations, 2 on second order polynomials, 3 types of composition for third order polynomials, and so on. We will recall how they affect the degree and then use them to redefine equivalently, but the new definition for first and second order polynomials that will then allow us to generalize to third and higher order polynomials and their degree. And then I probably will have already run out of time, so wrap things up by there. Let's start by recalling, the main contribution here is actually mostly definitions. And I'd like to borrow a proverb from Doran Seilberger, who famously said that a good lemma is worth 1,000 theorems. And I would like to kind of adopt this and hope that our definition is good and is in turn worth 1,000 lemmas. So polynomials. Polynomial growth, as opposed to exponential growth, for example, is often considered tame growth. So for example, in chemical reaction dynamics, this is not a polynomial chemical reaction dynamic. In computer science, the Cobham-Edmond thesis formalizes that polynomial runtime is considered equivalent with efficient running time. And in other areas of mathematics, such as pure mathematics, the finitely generated group, the famous Gromov theorem, characterizes the polynomial growth rate in such cases. So here you see some examples of polynomials, and they are subclassified with respect to their degree. So linear degree, quadratic polynomial, cubic polynomial, quartic polynomial. So lower degree means even more efficient, essentially. So what is a polynomial after all? Here you see an example. And here you see a general form of a univariate polynomial, let's say over natural number coefficients. Here's a formal syntactic definition in Backus-Naur form. Polynomials are generated, this class of expression generated by constant 1, the variable x, and whenever P and Q are polynomials, then so is their sum and their product. This is the syntax, and observe that we prohibit 0, that is a technical detail, and the semantics is obvious. It's just the semantics of natural numbers extended pointwise to polynomials, which means that a polynomial gives rise to a polynomial function, a non-decreasing function from natural numbers to natural numbers. Polynomials thus defined semantically satisfy commutative, associative, and distributive properties and the identity with respect to 1. So here are these properties, and we will use them now to redefine polynomials with respect to these rules, making them axioms. And these rules are thus by choice, they are sound, but they're also complete. Namely, using these rules, any polynomial can be transformed into this normal form above, so that this means the thus defined polynomials, syntactically defined polynomials, are exactly the same class as the ones that you already know. But now we have a formal approach. Regarding the degree is often defined using the normal form, looking for the highest non-zero coefficient. But here we want to take a different approach and redefine the degree of such a polynomial also by structural induction following the inductive definition, syntactic definition. So let's define the degree not based on the normal form, where it's obvious that the degree of the composition is the product of the degrees of the two polynomials, and instead define the degree of 1 to be 0, the degree of the variable x to be 1, the degree of the sum to be the maximum of the degrees, and the degree of the product to be the sum of degrees. So these are now axiomatic definition of the degree, and it raises the question, is this definition well defined? It could be that if we apply one of the commutative, associative, distributive rules to our polynomial without changing it, that then applying this inductive definition could give a different degree. But actually, turns out that the maximum operation, which is we use to define the degree of the sum, also satisfies commutative, associative, identity, and distributive laws, so that this means this inductively defined degree, which is of course the degree which you already know, is well defined. And I will spell this out in so much detail because this is how we then generalize it to second and higher order polynomials. So this new definition of polynomial requires to define the composition by structural induction, right? And then it follows that the semantics of the thus defined composition is indeed the composition as polynomial mappings. And the degree of the composition is, of course, then again the product of the degrees, but now with a different proof. Now let's move on to Arctic polynomials, and before that, tropical polynomials. What's a tropical polynomial? Tropical polynomial is one which involves the binary minimum operation and accordingly as neutral element infinity of the minimum operation. And there are some anecdotes where this adjective tropical comes from, but long story short, this is a common topic in mathematics, in algebra, and it's a special case of idempotent rings. And we're actually interested in the kind of dual to the tropical ring, and that's sometimes called the Arctic ring, where the minimum is replaced with the maximum, and the neutral element infinity is replaced with the neutral element 0. Here on the bottom, you see an example of such an Arctic polynomial, which involves said maximum operation. And we already recorded syntactic properties satisfied by the maximum operation, which will now turn into axioms, syntactic axioms for Arctic polynomials, which will be helpful later. So here is our syntactic definition of Arctic polynomial. And whenever we deal with an Arctic polynomial, I'm going to put this tilde on top of them to distinguish them from ordinary polynomials. That's the syntax. And the semantics is still obvious. It still gives rise to a non-decreasing mapping, but now it's not a polynomial mapping, it's an Arctic polynomial mapping. And first non-trivial thing is If you look at this maximal operation in the definition of the polynomial here, you can see that eventually, that is for large, when the variable becomes large enough, then one of the two arguments dominates. Put differently, for all sufficiently large arguments, the maximum can be actually eliminated, and the Arctic polynomial boils down to an ordinary polynomial. So to any univariate article polynomial, there exists a unique non-Arctic polynomial which agrees with the Arctic one for all sufficiently large assignments to the variable x. And we're going to denote that with the limit of the Arctic polynomial. There's no danger in confusing that with the classical limit from calculus, which is infinite in this case anyway, so not very interesting. And for example, the limit, the non-Arctic polynomial associated with the below Arctic expression is, I think, for all x larger than 6, it boils down to this polynomial, cubic polynomial, which you remember from the previous slide. So now we've covered Arctic polynomials, and we can move on to second order polynomials and their degrees. So second order polynomials are also now defined by Backus-No form by structural induction. They have constant 1 natural number variable n, and now an additional function variable phi. That's the syntax. And the semantics is that n is a natural number and phi is a non-decreasing function on natural numbers. And applications arise, for example, from computer science, runtime analysis of Oracle Turing machine, when the Oracle changes. So consider the Oracle as a variable, an argument. You can run the same Turing machine with different oracles, and the oracles we consider are not just Boolean valued. They don't just return yes or no, but they return strings. And if they return a long string upon a query, then it seems reasonable to allot more running time to the Turing machine, as long as it does not kind of exploit that. And this is this same setting. This is what is captured by second order polynomial runtime bound, namely to any such function oracle which maps binary strings to binary strings. We can associate such a function from natural numbers to natural numbers, namely the length of that oracle, the longest string returned by the oracle upon all queries of length up to m, and that's by definition non-decreasing. So this is the kind of phi we're considering, and this idea comes from Stephen Cook together with his PhD students Bruce Capron in '96 and Akitoshi Kawamura in 2012. Another type of application comes from calculus, from hard analysis. The proof mining program pursued, for example, by Ulrich Kohnbacher and Helmut Schwichtenberg, quantitatively refines theorems, statements, pi2 statements in calculus in terms of so-called moduli. Moduli are kind of Skolem functions of pi2 properties. For example, it could be a modulus of continuity of a function, or it could be a modulus of total boundedness for a compact metric space. So these also give rise to such mappings and translations between such classes of continuous function, amount to translations between such moduli. And if the translation is mild, then the resulting modulus will hopefully be bounded by a second order polynomial in the modulus of the argument. So this is where the examples come from. Also on the bottom of the slide, you see an example of such a second order polynomial. You see the first order variable n. You see products. Powers here are abbreviation for products. You see also the second order argument phi, and you see nestings of phi. So the superscript does not denote nesting. We spell out nesting that's just a convention. So this is thus designed second order polynomials, and they induce semantics, still satisfy the commutative, associative, and distributive law and the neutral element. And again, we turn these semantic properties into syntactic axioms, rules, such that they are sound by construction. And it turns out, but this is not rule, they're still complete if two second order polynomials are not syntactically equivalent under these rules. Then there exists an assignment which makes them actually evaluate differently. So sound and complete syntactic rules to define second order polynomials. Now let's define the degree of second order polynomial, picking up on our inductive redefinition of the degree from first order polynomials, now making a deductive definition similarly, but now we also need to define the degree of this new second order function type variable phi, which we'll define to be a first order, newly introduced first order variable d, so that the degree of a second order polynomial is an arctic first order polynomial. Not a number, but a polynomial, an arctic first order polynomial in the variable d. And again, we record that this inductive definition of the degree is well defined because of the properties of the maximum operation, which we've incorporated syntactically in the definition of arctic first order polynomials. I mean, these are the rules which then make the degree well defined. And as an example, the degree of the below second order polynomial turns out to be this long expression, the arctic first order polynomial that we already had as an example 2 slides ago. And remember that an arctic first order polynomial asymptotically agrees with an ordinary polynomial. So now we're already halfway through the presentation. Take away message. The degree of a second order polynomial is an arctic first order polynomial involving the maximum operation. For all sufficiently large arguments, arctic polynomials coincide with a unique ordinary polynomial, which we denote their limit, and the degree of that ordinary polynomial actually turns out to coincide with the nesting depth of the function variable phi. In the previous example, on the bottom you see here, phi is nested threefold. This is not nesting. Here it is nested only twofold. So the nesting depth here is 3 in this example, and this is not by chance. This is the degree of the asymptotic ordinary polynomial, which asymptotically coincides with the arctic first order polynomial, which is the degree of this given second order polynomial. Why do we do all this? The one main motivation is to specify second order polynomial growth in various degrees of conciseness and preciseness. Concise, precise. And to illustrate that point, let's review the example from the first order case. Suppose you have devised the algorithm for a famous open problem, and your algorithm is efficient, and you state that by saying that it runs in polynomial time, which is very concise. You could be a little bit more precise and say that the running time of your algorithm is bounded not by any polynomial, but by a polynomial of degree 12. That's why we talk about degree all the time. You could also be even more precise, but less concise by spelling out further that polynomial bound of degree 12. And you could even spell out the entire polynomial, including the polylogarithmic factor and including all constants, but that would be very precise, but very little concise. And with second order polynomial terms, we can do the same thing, but even more variations on the trade-off between preciseness of bound and conciseness. You could concisely say my second order polynomial is just a sum polynomial, or at the other end of the spectrum, you could spell out that polynomial, including all constants, which would be very precise but very long. But you could also just say the degree of your polynomial, like in the first order case. Remember that the degree here is now an ordinary arctic first order polynomial. You could be even more concise and specify the asymptotic of this degree, which recall is an ordinary first order polynomial. Or you could even be more concise and less precise by specifying the nesting deck, that is the degree of the limit of the degree, which is thus the number 3. So we hope, in the spirit of Zeilberger, that our definition of second order polynomial degree, now that we have shown that it is well defined, finds many applications in higher order computational complexity and outside in maybe proof mining. But now moving on to third and higher order polynomials, we recap the first and second order polynomial from a new perspective. And to this end, turns out that the polynomial composition will be the essential operation to generalize. So this is the previous definition, and the semantics is again given obvious. And observe that with this semantics, there are now two types of composition. One can, for example, plug in one first order polynomial instead of the natural number argument n of another second order polynomial. Or one could plug in one second order polynomial instead of the function argument of another second order polynomial. In both places, one could plug in another polynomial, which gives rise to two types of compositions. The first one we denote with the classical little circle. And for the second one, let's just introduce the notation star. And of course, these two types of composition need to be defined by structural induction, and then observe that their induced semantics coincides with the semantics that we expect from this simple little circle, the composition of mappings, right? And also, then again, it follows that the degree of the composition is the product of the degrees, where the degree of the first type of composition, the degree of the second type of composition turns out to be the first type of composition of the two degrees. Recall that the degree is an arctic first order polynomial, so we can compose them in an ordinary way. Now we take a new perspective on first and second order polynomials, taking the composition as a primitive operation, not as a derived operation. So this was our previous definition, and these were the properties which we turned into syntactic axioms. When we defined the composition by structural induction, we observed that this composition also satisfies certain properties. And then we defined the degree by structural induction in this way. And now we take as a consequence, the degree of the composition was the product of the degree. And now we take a new perspective. We introduce composition as an operator of its own right, similar to the multiplication and addition operator. And we turn the properties that we had semantically before now into syntactic rules, so that by construction they are sound. And actually, they turn out to be also complete. Namely, one can remove the now thus defined circle composition using these syntactic rules, and thus recover precisely the first order polynomials as we know them from before, so that these rules are complete. So now we have a new definition of first order polynomial based on this kind of composition. And I emphasize that because that's how we now going to also recap, review the second order case, and then we'll be able to generalize that in order to define, remember the contribution is about definitions, to define third and higher order polynomials. So this was our previous definition of second order polynomials. We observed that they satisfy some rules semantically. We defined two types of composition by structural induction. We observed that this thus defines compositions also satisfy certain rules semantically. And now we do the same thing as before. We turn these two kinds of composition into operators of the same quality as addition and multiplication, and make them axiomatic, turn the semantic properties into syntactic rules, and observes that now there is no application anymore of the second order variable phi, but the second order variable phi by itself becomes now one of the constructors with the same quality as the variable x and the constant 1. So these new rules we turn into syntactic axioms, so that by construction again they are sound, and it turns out that they're also complete. Namely, this defines the same class of second order polynomials just from a different perspective that we have seen before. Namely, to every thus now redefined second order polynomial, there exists one without the second kind of composition, using only the first kind of composition. And whenever the first kind of composition occurs, then its left argument is phi, which means this is the substitute for phi of polynomial p in our previous definition. So it's complete. And this is what allows us to generalize. But first, let's recall the degree, how we define the degree of second order polynomial, and now adapt this definition to this new definition. So now we define the degree of the composition to be the product of the degrees. So this is now not a consequence anymore. What is a consequence is that the degree of the second type of composition is a first type composition of the degrees. Yeah, we observe that in this new perspective of second order polynomials, every subterm is also of the type function type, non-decreasing function on natural numbers. So, for example, a variable x, when it attains a natural number value, then it is identified by occurring as a constant map. And now we're ready to proceed to the third and higher order case, which takes a similar second order case and which adds a new third order variable f, which is of type operator, and which adds so that now third order polynomials map operators to operators. Now the second order function argument becomes third order constant mapping. The first order variable becomes also a constant mapping. And now we introduce the degree the same way, we define the degree of the newly introduced third order variable to be a second order variable psi. And we also extend the definitions of the degree, first type of composition, second type of composition. But now in the third order setting, we have a third type of composition, which again can be eliminated, although the first and second type composition now cannot be in general eliminated anymore. And now the third kind of compositions, behavior and the degree, that becomes a consequence. The first and second kind of behavior now become axioms in our definition of third order polynomials. But I've already exhausted your patience enough, so let's wrap things up. We've talked about first order polynomials and their degree, giving various equivalent definitions, in particular based on structural induction, which turned out to be well-defined. Then we talked about Arctic polynomials, which asymptotically coincide with ordinary polynomials. Second-order polynomials, the applications in complexity theory and in hard analysis, syntax and semantics, and their degrees, having applications as a way of specifying asymptotic growth to various levels of detail and also various levels of conciseness. Then we recalled polynomial compositions, two types of compositions for second-order polynomials, and how they translate under our newly defined degree, which allowed us to reconsider first and second-order polynomials in a way that makes composition or compositions as first-class operators, not defined by structural induction, but axiomatically. And then that allowed us to generalize, to define third-order polynomials, and to well-define their degrees as Arctic second-order polynomials. And now you can imagine how the things proceed to fourth and higher order polynomials and their degree. For the details, please refer to our paper. And thank you very much for your attention.